Hello, um, this is Michel Devoret speaking. I would like first to thank the organizers for inviting me to present this review. This is going to be a short and opinionated review of hardware design for quantum computation. I would like to thank the Google team, the Google Quantum AI team, with which I did a sabbatical at Santa Barbara in the first semester of 2022. And some of the ideas that I will present at the end of this talk um, owe a lot to the discussions that I had with the team members. Okay, so this is the outline of my talk. I will first make an important point, I think. So Hartmut talked about superconducting qubits. I want to explain that superconducting qubits are manifolds of levels that are included in a bigger structure, a whole superconducting artificial atom. So to understand how we make our qubits, we have first to deal at this level of superconducting artificial atoms. And then I will explain what are the most popular atoms, the Transmon and fluxonium, and explain briefly how they work as qubits and compare them. And then I will end with a few remarks on, well, how should we choose our artificial atom? In what direction should we go to optimize them? So, as you can see, this is very simple. We are making circuits, superconducting circuits that behave like atoms. And on the left, I have chosen the simplest atom, the hydrogen atom, which classically you can think of an electron orbiting a nucleus. It now doesn't orbit, so the animation doesn't work. We had checked it, but it doesn't matter. On the right, you have the equivalent for our circuit. So as you can see, the unique electron that orbits the nucleus is now replaced by the whole electron condensate of the superconducting metal, which is used in the circuit. So C here refers to the capacitance of the two plates that you see with my mouse here. And on the left, you have a wire that connects the plates and which acts as an inductance. And as you can see, instead of the electron moving around the nucleus, what you have is a displacement of the electron condensate. So the electron condensate will slosh back and forth between the two plates, and it behaves exactly as a single charge carrier. So instead of an electron orbiting in 3D, in three dimension around the nucleus, we have a fluid that moves bodily inside the wire. And the correspondence is the following. We have the velocity of the electron around the atom, which here becomes a current through the inductor. And the way you can picture the force of the electron due to the nucleus now will be equivalent to the voltage across the capacitance. The main difference between atoms or ions and superconducting circuits are the dimensions. The dipole element for the hydrogen atom is about 1 angstrom times an electron charge. And for the superconducting circuit, you have pretty much the same amount of charge, but the distance is now of order of a millimeter. And with this increased dipole comes also a huge decrease in frequency, because, as you know, atoms and ions emit radiation in the form of light, visible light or UV, but here superconducting circuits emit microwave light. So it's basically 100,000-fold decrease in frequency. If we keep discussing this LC circuit, whose schematic is given on the left, we have essentially an harmonic oscillator. It's an electromagnetic oscillator, and like the mechanical one, it has energy levels. Interestingly, the distance between levels, which correspond to the transition frequencies between these levels, is given by a combination involving the value of the inductance and the capacitance. So instead of having a transition fixed by God-given fundamental constants, here we have just engineerable parameters for the circuit, for this quantum circuit. And like all harmonic oscillators, this circuit has wave functions, and interestingly, as plotted at the bottom here, for each of the eigenstates of the harmonic oscillator, you have superpositions of currents flowing in both directions for the circuit. Now comes a very important aspect, the question of dissipation. So we want to assemble circuit elements, but we want to avoid as little resistance as possible. And in order to understand this, is that you can think of resistance as broadening the levels. As you can see, the ground state stays sharp, but the first excited state is broadened, and of course this increases with level number. And so we can define a quality factor for the circuit, which is basically the lifetime of energy, or the decoherence of the first excited state here. So this is an important parameter for our artificial atoms, how good they are. And I'll come back to this point. In fact, what I said about dissipation being which should be avoided is not completely true. You need some dissipation, but at the right moment, because you need to reset the circuit in the ground state. You need to start an algorithm from a known state, and the ground state is preferred. And this is possible when you are at dilution refrigerator temperatures, given the frequency of our circuits. Now comes the big bonus of these superconducting circuits. So these artificial atoms, in contrast with the natural ones, are easy to couple. So one circuit can be coupled to several others. And the coupling can be capacitive, like here in this picture, or inductive, like on this picture on the right. And we know how to compute the Hamiltonian of this coupling as a function of the circuit parameters. So we can do basically Hamiltonian engineering. Now, what I have said about this LC circuit is, of course, a bit too naive, because the LC circuit has the unpleasant property that when you drive it, you can drive it in any way you want. You will never be able to go from the ground state, let's say, to the first excited state. So what you create, of course, is a series of transitions because all the levels are equidistant, and you can never control individual states apart from the ground state. What you need is to introduce non-linearity in the circuit. Basically, the potential energy needs to be anything else than a perfect parabola. And once you achieve enough non-linearity, all the transitions between levels become non-degenerate, and you can isolate the first two the ground and the first excited state for your qubit. And so this is where comes another very important design parameter, which is the non-linearity ratio, which is the ratio of the difference between, let's say, this 0-1 transition and this 1-2 transition over the transition frequency of your qubit. It is this gap here between these two transitions that will fix the speed of your operations. So you obviously want to have as large a nonlinearity as possible in principle. But comes another factor here. It's not only the distance here between these two transitions that counts, it's the width also of these transitions. So what you want to optimize is the product of the quality factor of your artificial atom times this nonlinearity factor. And so this is what the development of superconducting really artificial atoms is about. Now, how do we introduce this nonlinearity? Well, to my knowledge, there's only one really element that for the moment is better than everything else, and this is the superconducting insulator superconducting tunnel junction, which is just a sandwich of two superconductors separated by a very thin barrier. Someday, someone might invent another element, but for the moment, this is really our workhorse. Now, what does a tunnel junction do? Well, you can view it as a sort of nonlinear inductance, despite the fact that its symbol is a cross. If you plot the characteristic of this element, if you plot the current through it as a function of the flux, which is defined here as the integral of the voltage, you see that for small fluxes, it behaves like an inductance, a linear inductance, but it oscillates when the flux exceeds the of order the flux quantum. You can think also, instead of this flux current relationship, you can think also of this element as providing a potential, and because the potential is sinusoidal, it deviates comfortably from the parabola. Therefore, when we design a superconducting artificial atom to make a qubit, we can play with the combination of three elements, capacitances, inductances, pure inductances, and Josephson elements. It's a very simple Lego set, and you can go quite far into inventing all kinds of atoms, but you have to pay attention to important physical aspects. So each of these elements come with some defect. So in the capacitance that you might shunt your junction with, you may have some dissipative elements. People talk about nickname those defects two-level systems. You can have off-equilibrium quasi-particles, which are essentially broken Cooper pairs. You can have vortices, but you can also have parasitic emission of radiation, because those qubits are not alone. They are coupled always to at least a readout chain, and if you are not careful, information will leak through this channel. But things are improving year after year. We learned that this dissipative mechanism can be controlled in some ways, and each dissipation mechanism is associated with a quality factor. And you can see that on some defect, we can reach let's say, this figure of 100 million. We know how, for instance, we've learned how to control this quasi-particle dissipation. There is still progress to be made, of course. Now, if we think about the basic atom composed of a capacitance, a tunnel junction, and an inductance that combines all the basic bricks, how should we choose the value of these elements? Every element here, or these three elements, they come with a characteristic energy. There are some constraints, of course, on that we should respect on this energy. But these energies are going to create an Hamiltonian, are going to be the parameters in different terms of the Hamiltonian of this basic atom. And here I have written underneath the Hamiltonian of the hydrogen atom for comparison. You see that this term, which involves the charging energy of the capacitance, is a bit like the kinetic energy of the electron in the atom, whereas these two terms actually are like the 1/r potential of the hydrogen atom. I'll come back to the hydrogen atom in a moment. When you fabricate this circuit, you're going to fix these two aspect ratios. And also you have this knob here, which is the flux through the loop formed by the tunnel junction and the inductance. And by changing these parameters, you can change not only the shape of the potential, as you can see. By varying this ratio here, you can control the number of minima that you have in the potential. But by varying the capacitance, you can also change the number of levels per well in this potential. Okay, so now we come to this discussion of the various artificial atoms. There is a sort of Mendeleev-like table, if you want. Of course, these parameters these two parameters are very continuously, but researchers have given names to particular location in this domain, and each location is in a sense a particular atom with a particular set of levels and properties. There are two atoms that are distinguished here, the Transmon and the fluxonium, and they correspond to a sort of optimum. When you go in this diagram, if you go down, you lower the influence of charge noise. If you go left, you lower the influence of flux noise. And if you would go in diagonal, you would also change the influence of what is called critical current noise. To make a long story short, these two atoms are actually favored nowadays because, in fact, they minimize the overall influence of noise. You can view these two atoms in a very simple way. They consist of a small, rather low area Josephson junction, which is pretty much the same in both cases. But in one case, in the case of the Transmon, it is shunted by a large capacitance, whereas in the case of the fluxonium, this small junction is shunted by a large inductance. Where are we in terms of coherence, this famous quality factor? So here is a spectroscopic data of the hydrogen atom showing the let's say the qubit transition, the transition between the ground and the first excited state. It is actually a doublet, but we can focus on the main line. And we see that the quality factor of our textbook atom is 20 million. This is basically the width of the line compared with the transition frequency and inverse. And this corresponds to photon energies of 10 EVs. Now, if we go to the Transmon, we can do similar spectroscopy and see peaks like this. Of course, we have to be very careful because if we put too much power, the peak is broadened, so we have to lower the power. And if we go then to echo techniques, we can find that pretty much the Transmon has a quality factor these days of 10 million. We're not exactly at the level of the hydrogen, although in some experiments by luck people reach actually 20 million. But on average, it's fair to say that the current state of the art is more like 10 million. So I find it interesting that such a circuit with billions of atoms can rival with a natural atom. Now, optimizing this individual circuit is not the only thing that is important. In order to make a machine like the one Hartmut described, for instance, Google Sycamore processor, you need actually more than just good transmons or good fluxonium. You need actually to engineer coupling between those artificial atoms. And you need also not only to couple as many qubits to one qubit, that increases the connectivity and offers more possibility for your algorithm, but you need also to couple your qubit to a readout resonator and an amplifier chain. And so not only this quality factor here of the qubits are important, but you have also all other characteristics like the readout infidelity, the readout time, and the reset infidelity, the reset time, and of course 1 qubit and 2 qubit fidelity and time. And if we look at this table that compares the Transmon and the fluxonium, we see that the fluxonium is on the whole trailing behind, but quite close to the Transmon. In my opinion, because the fluxonium is not as is younger than the Transmon, still progress will be made in this column. But for the moment, something that is really a problem is that one knows how to couple a Transmon to 4 other Transmon, but so far for the fluxonium, only one other fluxonium has been coupled. So it could be that the fluxonium can actually represent an opportunity in an architecture where the check qubits, like for error correction, which are ancillars, they do not participate directly in the computation. The fluxonium may have a role there. The reason why you would not trust completely the table that I have just presented is that it forgets many other important design constraints. You want to reduce leakage. For instance, in doing an operation, you may leave the computational manifold, the 0-1 manifold. So that's a problem, and you have to design the circuits accordingly. Hartmut has told us about cosmic rays. This and other problems reduce the qubit actually operation time. It blinds all these events blind the qubit, and you have to wait until your qubit is there again. But there are also a lot of other constraints due to the fact that you are actually creating a very complex circuit with many qubits, like crosstalk and unwanted dissipative channels and a lot of other parameters. So it's a multidimensional parameter optimization, and there is really one question that I wanted to address at the end of this presentation is, well, I have said that non-linearity was a resource in those artificial atoms, but actually it is a dangerous resource. Of course, if you increase this relative anharmonicity, you have faster operations potentially, as long as, of course, you would not diminish coherence by increasing the non-linearity. But even then, even if you could maintain coherence, there's an additional important problem. As you increase the non-linearity, you also increase matrix elements between your qubit level, your computational manifolds, and spurious levels, which are not involved in your operations. Those levels are actually spurious. And so you have to manage all these spurious transitions. And if you reduce nonlinearity, actually this problem of dealing with this spurious effect becomes hierarchical. And so you can treat one effect after the other. And in my opinion, this is a much more comfortable situation to be in when you are doing this very large parameter optimization. Well, I have reached the allotted time of this review, and I will end by actually giving you two thoughts. This, of course, like all predictions, could be revised soon. But what I believe is that the present state-of-the-art technology of tunnel junction and superconducting circuits can be actually still optimized. And I think the goal of reaching a 1/10% for infidelity, for coherence limited infidelity to all operations, including reset and readout, which are very important operations for error correction. I think this seems to me possible. But to go beyond this kind of level of precision, I think it seems to me that breakthroughs in new material and device fabrication will be needed. For instance, one idea that has been floated is that our devices should not be made and then brought back to air like we do, but actually sealed, completely sealed in vacuum. On this note, I would like to thank you to your attention, and here I'm acknowledging my group at Yale, and with my colleagues, Rob Scholkopf, Steve Gervin, Shruti Puri, and Leonid Glassman, and our funding agents. And thank you for your attention again.